Okay, so this lesson is on section 13A of the textbook, and I want to start off by just looking at two of the examples in the textbook. And the first one is example number 5, part B. And I'm picking a simple one to start with because I want to kind of go through the process, describe a little bit about what it is, and then I want to actually see if I can give you something that is kind of like a definitive three-step process that you can use with these questions all the time that always works. Like a step-by-step what to do. Step 1, step 2, step 3. Anyway, so starting with this one here, it says that you're going to solve this equation. Sine 2x is equal to negative 12. And they want you to solve that where x is between 0 and 3 pi. So just to start off, I thought it would be nice to kind of look and see like what exactly is this question about. So here is a graph of sine x actually. So this is just sine x, and we know what it looks like, and it's roughly between 0 and 3 pi, which is just shy of 10 in terms of radians. So this is on the same scale, radians. And if you graph y equals negative 1/2, which is the green line, you can see where they intersect, right? So what they're asking you to do, and you can see there's 2 points of intersection, 7 pi over 6 and 11 pi over 6. So you can see that now, but the question is when sine is equal to sine of 2x, which of course what happens with the 2, so get rid of that and let's put sine equals 2. Actually, I'll keep that one, sine equals x, sine x. And here's sine 2x, and you can see that of course that would be your dilation of the period of the function, right, by a factor of 1/2. So there you can see that. So let's get rid of the sine x one, and we can see so sine 2x, since it has the period has been cut in half, then there's going to be more solutions, right? So when you're looking to see where it intersects with the line y equals negative 1/2. So now, of course, when we do this, we just saw with the solutions that it's fractions of 6 in the denominator. So when it says x is between 0 and 3 pi, that's equivalent between 0 and 18 pi over 6. So I just rewrote that there. Now, so we went over this. We looked at it in Desmos. So here's what the text does, right? So I want to go through what the textbook does, and then I want to make sure that you can understand what it's doing, right? So the first thing is that they take care of the domain, right? And that is to say that if x is between 0 and 3 pi, then 2x multiplied by 2, both sides, is between 0 and 6 pi, which makes sense. So that means that 2x, if you were to just use the unit circle, the angle, which we're calling 2x, the solutions that you see in the unit circle, if you're just going around the unit circle once, is just these two, 7 pi over 6 and 11 pi over 6. But then you're going further, right? You're going all the way to 6 pi. So you have all of the solutions. This is in the textbook on page 359, right? So I'm just kind of walking through their solution before I kind of talk about it in more, I guess, step-by-step terms, okay? So, so what they do is, once you know that, then you so this, if 2x is equal to that, then you divide both sides by 2, right? Because you want x equals. That's what you want to end up with. So dividing this side and this side by 2. So of course you have 1, 2, 3, 4, 5, 6 solutions. You're going to divide all 6 by 2 to get your final solutions, and that's what the textbook has. Okay, so, but I wanted to focus in on the second step that they did. So the second step, which is this here, where they get their solutions. Just to kind of focus in on where do they get that from. So in that second step, basically they're asking themselves, okay, where is sine equal to negative 1/2? Forget about the fact that it's 2x. Like, where is sine of a theta, an angle, equal to negative 1/2? So in the unit circle, So of course the unit circle goes around 2 pi times, right? 1 pi, 2 pi. This says go up to 3 pi, but you can see on the, if you go around half a turn here, another half a turn to get to 3 pi turns around, this one doesn't add any more solutions. So the only two solutions that we have is in the going from pi to 2 pi, and that's where you get your 7 pi over 6 and your 11 pi over 6. So for x, between 0 and 3 pi, those are your two solutions. That's the original solutions that you get. But of course, we said from the beginning that we're looking for 2x is what the angle is. So the angle being 2x, that means you multiply this by 2. So you multiply this by 2 and this by 2, but that's 0. So basically, we're going around this many times, right? So 1, 2, 3, 4, 5, 6. So you can see that we're going to be adding 4 more solutions. Like you can see that by just looking at how many times we have to go around, because we have to go around this many times. So how you get those solutions, you start off with your original solutions, 7 pi and 11 pi over 6. And of course the period of, right, sine is 2 pi. So you take one of them, 7 pi over 6, and you add 2 pi to that, you get the 19 pi over 6. You take the 11 pi over 6, you add 2 pi to that, you get 23 pi over 6, etc., etc. And you do that, and that's how you end up with all of these solutions, right? You're going around until you stop at 6 pi, right? You don't want to go beyond that, because that's as far as they told you to go. So what I would like to do is I want to offer you a suggested approach for all of these questions. Now that one that we just did was a very simple question. There was only one adjustment or one transformation made to the x values, and that was just multiplying it by 2. But of course other things could be done, and there are other examples of that, but this one just had the one transformation. So it's very simple, but I think I want to walk you through, this is my suggestion, and I have a little acronym, which I don't usually do, but I came up with an acronym, so, you know, if it's cheesy, just blame me being a dad, and I do dad jokes and stuff like that. So anyway, it's a bit cheesy. So here's my suggested approach. For the same 3 steps that they did, so notice that they did do, in the end, they did 3 steps. So there's this first step where you adjust the domain. There's a second step where you come up with your solutions. And then there's this third step where you basically, you solve, right? Because over here you don't have x equals, you have something else. So then you want to convert that to x equals, right? So here's my, what I'm calling those steps. Step 1, I'm calling it substitution, and you'll see why in a second. But basically we're taking care of the domain, right? Same thing that they did. Step number 2, I want to find preliminary solutions, which is exactly what they did. And then you're going to take those solutions and you're going to do, in that case, all you had to do was divide by 2 to get your final solutions. And that's step number 3, okay? So substitute, preliminary solutions, and finally final solutions. So my acronym for that is SPF, as in sunscreen. So we'll see how that goes. So let's do that same exact question, 5b, again, but actually going through the steps, and then I'll do a more complicated one so that you see how versatile it is. So you were asked to do this. So what I'm going to suggest is, actually, you can look at it as a substitution. This 2x is the angle, right? Sine of whatever, sine, cosine, tangent is always of an angle. So the angle is called 2x. Let's actually substitute that. Let theta equal 2x. So, of course, if you were asked the question, sine theta is equal to -1/2, well, you know right off the bat from the unit circle, you know what your solutions are, right? But anyway, let's finish doing this first step here. So I'm actually showing it as a substitution. You don't have to. They didn't do it that way, but I think it's somewhat helpful to think through the process, especially this part here. Now, you still have to adjust your domain, right? So if x is between 0 and 3 pi, which was given, then you know that your theta is between, because theta is 2x, you have to multiply by 2. So the theta is between 0 and 36 pi over 6. Okay, so that's step number 1. So step number 1 is I substituted, but I'm attending to the domain. Step number 2, I'm going to get my preliminary solutions. So my preliminary solutions are, again, the same approach that we said before, but I'm starting from here, and I'm saying, okay, sine of theta is equal to -1/2. Here's my first solutions. Just as before, I know that the period of sine is 2 pi, so I'm going to add 2 pi onto those until I get to here. I can't go any further than that because that's it. But when I say theta is equal to all that, what I'm saying now, all of that is equal to 2x, right? So I could have put the 2x over here, right? 2x is actually equal to all that. So you have your final, step 3, is your final solutions. You still have to do the same thing that we did before. Like I said, I'm just doing it over just to introduce the idea of these 3 steps. Now we'll actually do it with a little bit more complicated question. So the more complicated one is this one. Let me just get that here. And that's example 7. So that's on page 360 of the textbook. Okay, so it says tan of 2x minus pi over 3 is equal to 1. That's the question. And they're saying for x between negative pi and positive pi. So let's do the steps. Step 1, let theta equal 2x minus pi over 3, because that's what's in the bracket. So I'm going to do that, and I'm going to say, well, then the question becomes, the question basically becomes this, down here. Tan of theta is equal to 1. But we have to take care of the domain, right? So the domain they gave us is between negative pi and positive pi. So on the lower side, if we take this, 2x minus pi over 3, and you apply that to negative pi, you get negative 2 pi minus pi over 3. And that's on the lower part of the domain that they've given you. Which is, now I'm going to convert that into thirds, and you'll see in a minute I'm going to actually convert it into twelfths, because just to get a common denominator for everything, necessary for adding. On the upper side of the range, or domain rather, I had pi, so I'm going to apply this, right? 2 times pi minus pi over 3. So I get 5 pi over 3. So here's my really restated. So what I'm doing is I'm restating the question. I'm saying this is the question. Tan of theta is equal to 1 when theta is between negative 7 pi over 3 and 5 pi over 3. So pretend like this is the original question that you're given, and now you're going to go ahead and do it. Well, so from the unit circle, again, we know that solutions to this is where tan is equal to 1. Well, that's going to be in the first and the third quadrants, pi over 4 and 5 pi over 4. So there's our very, very initial going around just once solutions. Now, because I have quarters here and I have thirds here, I'm going to convert this to twelfths, right? I want to have a common denominator, so I'm speaking the same language throughout the whole thing. So when I said here that theta is between negative 7 pi over 3 and 5 pi over 3, I'm saying, well, that's the same as negative 28 pi over 12 and 20 pi over 12. Okay, so I'm going to go to step number 2, which is, let's come up with all of our preliminary solutions. All right, so our first 2 solutions were these two, 5 pi over 4 and pi over 4, which is, again, I'm going to convert that to twelfths because I want to have a common denominator for everything, right? And I want to know now all the solutions that are between negative 28 pi over 12 and 20 pi over 12. So now the period of the tangent function is pi radians, right? So I'm going to take these 2 solutions, here they are restated in twelfths. I'm going to take these 2 original solutions and I'm going to go up and down pi radians from there, right? So pi being, 1 pi being 12 pi over 12, again, just to keep everything in the same unit of measure, right? So because the period of the tangent function is pi radians, right? So here we go. I can write down my first two solutions, which are 3 pi over 12 and 15 pi over 12. And I'm going to go up and down, adding 12 pi over 12 or subtracting 12 pi over 12 from there to get all of the solutions. But within these bounds, right? These are my boundaries. Now, the 15 pi over 12, if I were to add 12 pi over 12 to that, I would go above. So I'm not going to go further. I can only go back, right? So I start at my 3 pi over 12, and I'm going to subtract, and I'm going to subtract again. Subtract 12, subtract 12. So I get, these are all my solutions. 1, 2, 3, 4 solutions. And now, all these 4 solutions, of course, well, that's equal to theta, what I call theta, but that theta is equal to 2x minus pi over 3. So now I can move on to step 3, and that is, what are my final solutions, right? So if 2x minus pi over 3, which again, just to restate it, because, you know, we have to have a common denominator to do any adding or subtracting. That's the same as 2x minus 4 pi over 12 is equal to all of these things. And now I'm going to solve, just like you solve any other equation at this point, except that there's 1, 2, 3, 4 solutions instead of just one. So the first thing I'm going to do, of course, is I am going to add 4 pi over 12 to all of these solutions. Voila, right? So from here to here, that's all I did, was I added 4 pi over 12 to each of those solutions, and this is what you get. And then the last step, I'm going to divide by 2. So everything gets divided by 2, right? So from here to here, I added my 4 pi over 12. And from here to here, I divided by 2. And that's how you get your final solutions, okay? So this can be a little bit confusing at first. And so, of course, you have the textbook and how they did it. I like adding, it might seem like a little bit of, and it is a crutch, a little bit of a crutch where I kind of have these steps, and I'm introducing like a substitution where do you have to introduce a literal substitution and say let theta, let theta equals the 2x or whatever is in the bracket? No, you don't have to do that. But I think it's a nice approach that you can take every single time so that you don't forget anything. These kinds of things, acronyms are really good, of course, so that you don't forget anything, right? Which could very easily happen here, right? So I just wanted to offer that to you. So the last thing, what I'm going to do, of course, I'm going to upload this all of the documents related to this. What I'm going to do is I'm going to also, I did a couple of the homework questions where it's actually my work doing it, and where I'm adding in, so this is, for example, is homework question number 6J, and I'm adding in, here's where I'm doing step 1. I'm actually doing it that way. Here's where I do step 2. Here's where I do step 3, etc. So I did a couple of questions, 6J and 8B, I did that way, right? So that you can actually kind of walk through the process. But in the end, the important thing to remember is that in the end, this is what we're doing, right? So part 13B, gets into actually, actual like word problems related to this, right? So, but what you're doing in 13A is that you're finding these solutions, right? So this sine wave could represent anything. It could represent, time versus height for like a merry-go-round or whatever it is, or it could be literal waves, and it could be a buoy bouncing up and down, and they can ask you a question related to that, right? So, and I think you've seen those kinds of questions before last year, but now perhaps you can have a little bit more in terms of the transformations that are added to it and how many of these solutions that you might be asked to do. So you could look at it graphically, and you can also look at it algebraically, which is what we just did, and you find your solutions. Okay, have fun, enjoy the homework, and talk to you next time.